There we go. Alright, so YouTube is up. And we still got about 2 more minutes. Alright. Just want to see if there are any questions coming from reviewing the material over the weekend, the long weekend. So in the past, and I'm gonna keep probably about the same process in the past. I have a script to distribute a Google Doc that is specific to each individual in the class. And that will be done, the script starts running about 5 minutes before noontime. So it takes about, I would say maybe, it depends on the server load, but it takes about a minute to run the script. So you guys will all get your exam before noontime, and then you just write in the same document. At least that's what I did in the past. Is you would basically just write under the questions, to put your answers in, and then at about 1:20, my script will run again, and this time to unshare the document. So that's typically how it goes in the past. But because there's an issue with equations, the use of equations in Google Document, I may change it so that you have one document as the question, and then you have another Google document as to collect the answer. So I haven't really quite decided yet which way I want to go with this semester. But you can count on having a document shared with you to collect the answer, and then the document will be unshared at the right time. Yep, sure. All right, 20 more seconds.
He said 20 more seconds.
Yep. Because it starts at noontime. Alrighty. So we're gonna get started now. Because there are no questions regarding the topics that will be in exam 1, I'm going to proceed to talk about a new topic, which is relations. Relations, hopefully you have had some time to read this module before class. So a relation is really kind of interesting, because a relation is basically is really just a subset. Okay, it's just a subset of the Cartesian product of a set X with itself. So R is said to be a relation over X in this case. So it's really not that complicated. Okay, so let me just kind of give you some examples using the tablet here. Question? Nope. Okay. I thought I heard somebody wanting to ask a question. So let's just say that X, as a set has elements 0, 1, and 2 in it. So a relation R that is defined over X is really just a subset of the Cartesian product of X with itself. In this example, okay, this can be a relation. You can have an empty relation R over X, because the empty set is a subset of the Cartesian product of X with itself. You can have, just kind of anything. Okay, you can have 0, 1, and a 1, 0. Okay, that is a relation as well. Now, why do we have this relation where 0 and 1 is in it, and 1 and 0 is in it? I do not know. Okay, but it is a relation defined over X. Okay, so that's kind of the terminology that we use in this class. Is we look at a relation as a Cartesian product of a set with itself, and when that is the case, we say R is a relation over X. So do we have any questions about those terms? R is the subset of the Cartesian product of a particular set X with itself. Okay. So the other way to say that is, whether a element is relating to another element in a particular relation. Okay, and I'm moving on to the notation perspective. So I'm moving on to this particular paragraph at this point. So using the example that we have already shown here, let's not look at this example, okay, because an empty relation is not really that much fun to look at. Okay, so we'll look at this R that is defined over this particular X over here. So in this case, we can say 0 R0 is false. 0 does not relate to 0. Yeah, I palms, it detected my motion, on my palm, so I'm gonna turn off swipes. There we go. Alright. So 0 R0 is false because according to this relation, 0 does not relate to 0. On the other hand, if I say 0 R1, then it is true because 0 does relate to 1 because we can see the 2 tuple 0, 1 over here. Let's look at another relation. So in the other relation, we have 0, 1 as a 2 tuple in it, and then we have 1, 2 as a 2 tuple in it. So in this case, 0 R1 is true, but then 1 R0 is false. In other words, the ordering of elements within a 2 tuple is significant. Okay, the first one is said to relate to the second one in a 2 tuple. Let's go with another example. Okay, so this is another R, and this time we have 0, 0, and 1, 1. Okay, and that's perfectly okay because in a 2 tuple you can have the same value appearing more than once because ordering is important in this case. So in this case, R0 R0 is true, 1 R1 is true, 2 R2 is false. 2 does not relate to 2 because I cannot find a 2 tuple with 2 2 in it. Alright, so are there any questions about these concepts? Basically, we are just introducing the various ways of expressing whether an element in X relates to another element in X by looking at the relation as a set of 2 tuples. Alright, I'm not seeing any questions in the text channel. Then we're going to move on and we'll use a concrete example in this case. So the concrete example is using the relation less than. So less than, which as a comparison operator, is basically a relation. So anytime you can have an operator that takes two particular elements and it returns either true or false, you can kind of see it as a relation. So less than is a relation. So if we are to look at less than as a relation and look at it as a set, then we know 1 is less than 2 is true, but then we will also basically say 1 2 as a 2 tuple is an element of less than as a relation. So to make this example a little bit more complete, let me just go ahead and use the tablet. Okay. So in this case, we have less than, I'm just keeping less than as a symbol, but this time it is the name of a set, okay? It is a subset of, in this case, because we're comparing integers, so it becomes a subset of the Cartesian product of integer Cartesian product with integer. In this case, if you want to look at less than as a set, okay, let me erase that. Then you can see 1 2 is in the set because 1 is indeed less than 2, but then 2 1 is not in the set because you can also say the membership is false. 2 1 as a 2 tuple as a member in the set less than is false. Well, that's because of our common understanding of what less than means, but we are looking through, we're looking at less than using the context of a set in this class. So do we have any questions about any one of these terms or concepts before we continue on with the module?
I think I have a question.
Yeah, go ahead.
Okay, so I understand that we are getting the set of um of integers and taking a Cartesian product with that.
Mm-hmm.
So less than, what is the number that you're referring to with less than? I'm sorry. Are
So
you referring to the set above? I'm just having a hard time understanding why the 2
mm-hmm.
isn't going to be a Cartesian product with itself when above we have 0, 1, 2 as like numbers trying to say.
Okay, so let's go through all of these symbols. This is this part here, this funny looking z is representing the set of all integers, and so is this one. And then this symbol here is the Cartesian product symbol. So on this entire side, if I were to use extra parentheses, we are looking at the Cartesian product of integers with itself. Is that okay? And that
Yes,
includes, yeah, that includes every single way to pair any integer with any other, with, I shouldn't say any other, with any integer. So you can have 0 paired with 0, 1 paired with 1, 2 paired with 1, 1 paired with 2, and so on. So that includes all the possibility. This, on the other hand, on the other side of the less than, excuse me, with the subset of, this is basically just representing a set. It is a funny looking name for a set, but I'm just using it as a set notation. Is that okay? In other words, this thing here is not being seen as an operator anymore. It is being seen, at this point, only as a funky name of a set.
yeah. What I guess, so okay, yeah, I'm tracking all of that tracks.
Mm-hmm.
Okay, if you don't mind, if you can just continue, that all tracks for me.
Okay,
I
all
don't have
right.
a problem with that. I have a problem with when you're evaluating
Mm-hmm.
2 comma 1, because to me those are integers, and those
Yes.
are an integer found in that set, the fancy z. So in my mind,
Mm-hmm.
that should be considered a subset of the Cartesian product because those numbers are
Mm.
found.
Nope. Okay, so I think you're mixing the concept of membership with the concept of subset, because z cross z looks kind of like this. Okay, it is a set of 0, 0, 0, 1, 1, 0, 2, 1, and so on, right? There's an infinite number of items in it. But you can see that 1, 2 as a 2 tuple is an element of um, of a subset, which is the less than subset, which is in return a subset. It is an element. Okay, let me rephrase it. 1, 2 as a 2 tuple is an element of a subset that we call less than
Hmm.
of z Cartesian product with z.
Hmm. Right. So, like right now, when
Mm-hmm.
I'm looking at the way you wrote up the Cartesian product, the very
Mm-hmm.
last value is 2 comma 1. So I'm like thinking, okay, write this out like how you did up there. And when I see that value appear, I'm thinking that okay, the subset, like the subset less than, I guess I'm just missing the condition that makes 2 comma 1 fall from the true category, because I'm writing like the Cartesian product out above you, like how you written, and
Mm-hmm.
then when I evaluate what the less than subset uh, is, less than subset is Cartesian product of the integers of all integers. It just, it feels like it should be included, but I'm missing what the condition is
You
that makes it not, because
are
I'm
you?
writing
Oh,
the
okay.
Cartesian product
So your
and
question
seeing
is
2 comma 1 in there.
So your question is, why is 2, 1 not an element of the subset of less than as a
Yes.
set? Well, because
Hmm.
2 is not less than 1. 2 is not less than 1, because the relation less than is used to express whether an element and an integer is less than another element, and it goes from left to right. In other words, when we evaluate a 2 tuple, we are basically asking in this particular case whether the first item of the 2 tuple is less than the second item in the 2 tuple, and that's why 1 2 is in the set and 2 1 is not.
Thank you so much for explaining that.
And Tom is okay. So Tom is correct in this particular case because of the way that I want the relation, because of what I want the relation to express. Xy is in the set of less than if and only if x is actually less than y. So to refine what Tom said, okay, we're gonna use this here. So x, y, okay, so we'll use quantifiers too. So we'll say for all x, y as elements of the set of all integers, xy as a 2 tuple is in the set of less than. I know Aiden wants to use a letter for this, but yeah, because the module is already using the less than symbol as the name of the set, I'm just going to use that for now. If and only if x is less than y. So I don't want to use the less than symbol here, so I'm just going to say it is less than y. There we go. So this is the property that I want in the less than relation. So it's basically how it is defined. All right. Cool. All right. So assuming there are no further questions about this. If you do, just let me know. But assuming there are no further questions about this, I'm gonna take a break here to explain why this is important. Okay, so relations are important because we like sorting. We like sorting algorithms because sorting algorithms help us rank things in a sequential order, in a linear order, and that is it's useful in many situations. Okay. So we're going to use an example of a gaming engine or a particular game, okay, where people go online, they play their games, and at the end of the day or at the end of a week, they would announce, gamer of the day or gamer of the week or something like that. Okay. So now the question is, what do you use to evaluate, gamers against each other to determine who is the gamer of the day? Well, there can be a lot of factors, right? Depending on the company and depending on the nature of the game, there can be a lot of metrics that people want to take into consideration. So now the question is, how do we combine all of these factors? So the way we combine these factors, to determine, who is quote unquote a better player than, who else, that relation may have certain properties or it may not have certain properties. So at the end of the day, we want to know whether a relation is partially ordered or whether it is totally ordered, because those two specific properties of a relation can determine whether things can even be sorted or not. So that is the importance of understanding relations and also different properties of a relation. So I'm just I'm just giving you a rationale of why we are talking about this topic, because a lot of times we get absorbed in the mechanics and all the details and all the mathematical symbols, but not kind of remembering why we are talking about this. So that kind of gives us a context of why this particular topic is important in computer science. Section 4, basically just talks about a random example. So in the random example, we have x itself has 4 elements, just a, b, c, d. And we can define a random relation. Yes, in other words, this relation has no particular meaning. All I want to do is to illustrate, various ways of describing how members of X relate to each other or not. So we say ARB is true because AB is a two tuple in R. So we say ARB is true, or otherwise we can also say A does relate to B. We can also say that BC as a two tuple in R is true because BC as a two tuple is indeed in the set that we call R. We can say BRB is false. B does not relate to itself because BB is not in this particular set. But we can also say that a two tuple DC in R is also false because when we look at all the elements in R, DC is not in it. So this part is really just a terminology kind of thing. So the rest of the paragraph talks about, so how many relations can we generate when we have a set X that has only 4 elements? That's the question, right? So the way we answer that question is we first understand, how many two tuples, we can create when we have a Cartesian product of X with itself. So that will just be 4 times 4 because everything in X can relate to everything in X. So we have a total of 16. Let me go back to the tablet so this way I can kind of illustrate what I mean by that. Alright, so we'll say X is a set. It has one of A, B, C, D in it. Alright, so now we say X Cartesian product with X, that the cardinality of this is 16. Are we okay with this? Because we have AA, AB, C, AA, AB, AC, AD, BA, BB, BC, BD, CA, CB, CC, CD, DA, DB, DC, and then DD. So those are the 16 elements in the Cartesian product. But now we want to ask, how many relations can we generate out of this? Now in this class we never really kind of talked about power set. Okay, so a power set is basically the set of all the subsets given a particular set. Okay, so the power set, which is kind of a funny looking P of X, is basically the set of all subsets of X. Okay, so now if we want to look at the power set of X Cartesian product with X, we are only interested at this point with its cardinality. So the cardinality is going to be 2 to the power of 16 in this case. That has to do with every single element in the Cartesian product can be present or absent in a subset. So if you think about present being a 1 and absent being a 0, and then each particular subset, each particular element in the Cartesian product as a position in a bit, then we have basically a 16-bit integer. And with a 16-bit integer, there are 2 to the power of 16 possible values. So we are talking about, 65,536 in this case. So that's kind of interesting to know because, it really kind of tells you, the just in terms of magnitude, when you are given a particular set X, how many subsets, how many relations can we generate out of this kind of simple set of only 4 elements? The answer is there are 65,536 relations that we can generate. Now, how many of those relations is actually useful or meaningful to us? Probably not a whole lot, but that would still be the answer. So every time you do a power set, you're basically raising something to raising 2 to the power of the cardinality of the set that you're making the power set out of. Oh, infinite power set. I'm not sure whether that thing does exist or not, because infinity is a funny thing. It is not actually a value. It is a concept, but it's not a value. Alright, so we are now getting into the really, really important part of this module, and you can see that we are kind of right in the middle of the entire document. So these are properties of relations. The first one is called reflexive. Okay, we basically ask, is a relation reflexive? And the definition is, if a relation is reflexive, I'll take it back. A relation R over a set X is reflexive if and only if this particular statement is true. So what is this statement saying? If you read the statement from the outside in, we start with the universal quantifier. We basically say for each element of X, for each element E in X, EE as a 2-tuple is in R. Okay? If that is the case, then R defined over X is called reflexive. Alright, so let's use some examples to illustrate this. I'm just doing on the side, adding a new page to the whiteboard. Alright, there we go. So let's go ahead and kind of think about what that means. Okay, so we'll start with something simple. Okay, we'll start X with only 2 elements, because 3 is already a lot. I mean, 2 is sufficient to illustrate the point here. Okay, so X itself only has A, B as elements in it. So now we'll look at possible R's, or some specific R's that we want to look at. So the first one is an empty relation. So now the question is the empty relation reflexive? Well, let's check out. Let me just rewrite what qualifies a relation as reflexive. Okay, for all E in X, we want the 2-tuple E to be in R. So if this is true, if and only if this is true, R is reflexive. Okay. So now that we have the definition also on the same slide, can someone tell me whether this particular R is reflexive or not? It is not reflexive. Very good. So now I'm going to ask the next question, which is, why do you think it is not reflexive? Well, those are indirect answers, but you can also give me just an example. Just give me a concrete example and say, since this thing is missing in R, R cannot be reflexive. Okay, you can say because not reflexive because you can pick one. Okay, you can say AA in R is false. That's it. Okay, because in order for R to be reflexive, AA and BB both need to be in R. Alright, so let's look at the next one then. We got AA, we got BB, and that's it. Okay, is this reflexive? Yep, that is correct. It is indeed reflexive. And then we'll look at a third example, which has AA, AB, BB. Okay, is that reflexive? Why is it not reflexive? All right, but why is the presence of AB in R making it not reflexive? So this kind of really goes all the way back to the understanding of the universal quantifier, as well as the concept of membership. It is reflexive. Exactly. So Jonathan is correct. Jack is correct. Um, Having the extra element of AB in R doesn't do anything bad to the definition of whether it is reflexive or not. Alright, so I want you guys to think about this in a loop. Okay, so what we want to do is to think about this in a loop. Okay, and the loop is generated by this expression. Okay, so for all e in x, okay, so the first e, the first value, the first element we can bind e to is a. Okay, and when that happens, we say a is in R is true. Okay, very good, right? And then in the next iteration, we say, give me another value, give me another member in X so that we can bind E to that other member. So now we say, that's the other one, which is B. But then when we evaluate that condition, BB is in R is also true. And then when you go back to the beginning of the loop and say, hey, give me another one, the loop is going to say, nope, this is it, right? There are only two elements. We have evaluated this condition for every element in X already. And for every single element in X, the answer is true, right? So now we can conclude and say that, hey, this R is also reflexive, because AB is never a part of the evaluation or the qualification of whether this specific R is reflexive or not. In other words, this is sort of a trick question, but sort of not a trick question. It is really here, so that I can see whether you guys can focus on the actual definition of whether a relation R is reflexive or not. Do we have any questions about this? Why, in the third example, this R is indeed reflexive? Are we good so far, or are there any further questions about this?
I have a question just to expand on
Yeah.
this example.
Yep.
So if you had added the two tuple a comma c.
That cannot be, because C is not even an element of X.
Oh, okay. I'm sorry. If we adjusted the set x, added c, and then added the two tuple a c,
Mm-hmm.
because c is in the y position, would we not evaluate it and it still evaluate to true because?
No. So in that case, okay, so if I understand correctly, you want, so this is an entirely different example where X is ABC, right?
Correct.
And how do you want to define R?
Copy the very bottom R with AA two tuple, AB two tuple, BB two tuple,
Mm-hmm.
and then at the end of that add a, or I mean I guess this is not the AC as the fourth two tuple in that.
Okay. So let me try to capture that first. So what would be the last one?
A comma C.
A comma C. Okay. So in this case, R is not reflexive. It is not reflexive not because of the presence of AC, but because of the absence of CC. Because in this case, if you think about this from the loop perspective, when we say for every E in X, okay, this E will bind to element A, it will bind to element B, it will also bind to element C. When E is bound to element A, AA is in R is true. When it binds to B, BB is in R is true. When it binds to C, then CC is in R is not true. And since we have at least one item that is making the condition, the universally quantified condition, being false, so the entire statement is false.
Thank you for going over that.
Yep, sure. So So that particular question relates to how we evaluate the for all symbol, because you basically have to, and how the for all symbol influences what expression we are actually evaluating for each quote unquote iteration. I'm using the concept of a loop and iteration simply because this is a computer science class and we are all familiar with the concept of a loop. To mathematicians, on the other hand, this is not a control structure. Okay, they don't do things sequentially. They basically, it really is just an abstract concept of, is it true or is it not true that for everything in this particular set the following condition is true. So I'm adapting that concept, the mathematical concept, to a loop concept, because in this class we are all computer science students, or most of us are computer science students, and as a result we are more familiar and comfortable with the concept of a loop than simply a abstract concept of for all. So that's the kind of the bridge that I'm trying to make with this class. But don't tell a math professor, yeah, well, we want to see this as a loop, and as we go through each element in the loop, nah, your math professor is not going to like that. So I just want to make it very clear that this is a specific way for me to explain these concepts, because we are familiar with the concept of a loop. All right. So let's move on to symmetry. Okay, in other words, we're asking whether a R defined over set X is symmetric or not. Okay, so I'm just going to read the English version first, and then we'll take a look at a few examples. A relation R over a set X, you can see that phrase is used all the time, right? Is symmetric if and only if, and you can see the word if and only if is also used a lot. Okay, if and only if is very important in this case, because we want to basically equate whether this expression is true or not to whether the relation is symmetric, whether it is symmetric or not. Okay, so it is important to use if and only if in this case. So the quantified expression is a little bit different. For all EF in X, EF in R, if and only if FE in R, is how we qualify whether a relation is symmetric or not. So this is where we're going to run in some really kind of, I would say, initially it is going to be counterintuitive sort of stuff. And then Aiden typed in the text channel, is there such a thing as strict reflexivity and strict symmetry where there are no elements that don't follow the rule? I'm not really quite sure what that means. Oh, you mean it excludes things that do not follow the rule. So it doesn't contain anything extra. I do not know. To answer the question very honestly, I do not know. I would assume it does not. It depends on whether there's a need for strictly adhering to the rules, and it really only applies to reflexive, because for symmetry it does take a look at every single item, all the possible pairs. It's just evaluating a if and only if statement for every single possible pair. So I'm not sure, but I would suspect there's no need of the strict version of these qualifications. All right, so let's open a new page. You can't see it yet, but I'm gonna switch over to the tablet. Oh, before I switch over, I'm going to copy the expression. So we say for all EF, I'm copying, you cannot see it, but once we switch, you can see it. EF, oops, one too many. EF in R, if and only if FE in R, and Alright, well, I got some extra parentheses, but it's okay. It doesn't hurt. It's just, some extra stuff. Alright, so in this case, we'll say, let's define x to be simple again. So we'll only have a and b as elements in x. And just like before, we evaluate the empty set. So now the question is, okay, so let me kind of add this. Symmetric. There we go. So now I want to ask, is this R symmetric? It is a very tricky thing. It really depends on whether you understand, whether you can connect all of those concepts that we have talked about so far. Okay, so the first concept is the quantifier. Okay, the second concept that is super duper important in this case is the meaning of if and only if. Now we did talk about if and only if as a Boolean operator. I think that was in the first class? Yeah, I think we did talk about it in the first class. But the importance is really shown in this particular definition. The answer is true. Yes, so Jack is correct that an empty relation is indeed symmetric. But there's nothing in it, right? But that's okay. Having nothing in it guarantees that both sides of the if and only if has to be false, right? Because R is empty. So neither this element of nor this element of can be true. They both have to be false, regardless of which E and which F we choose from X. And then false if and only if false is true. And as a result, every single way you bind E and F to elements in X will make this particular expression true. And as a result, by the definition of symmetry, an empty relation is indeed symmetric. Are we okay with this one? If you need more time, let me know, because it is a little bit tricky. If anyone wants me to use the loop concept to look at this, we can sort of do that. I will kind of do it, initially, just so that we get a hang of, how to interpret the for all quantifier, and also, maybe even the existential quantifier. But then, later on in the semester, we'll try to avoid the use of a loop concept to understand notations like this. Alright, I'm not seeing anything in the text channel, so that means everybody is getting this. Okay, alright. Let's look at the next example. So we got AA and BB this time. And you guys go like, oh, we know this one is reflexive. Yes, it is reflexive. R is reflexive in this case. But the question is not whether it's reflexive or not. The question is whether it is symmetric or not. So what do you guys think? Yes, it is. Yes, indeed. So this is symmetric, and so is this. Very good. Let's look at the next one, which is a little bit tricky, because now it is not reflexive. But is it symmetric? Remember, our current context is whether something is symmetric or not. We don't really care about reflexive at this point. Is this one symmetric? It is indeed symmetric. Let's try another one. This one has AB. Oops. Okay. It has AB and BA in it. So is this one symmetric? it is symmetric. Okay. All right. So let's take a look at one more. We got AA, BB, and then just AB. How about this one? Is it symmetric? The answer is, yep, Jack is right. It is not symmetric. It is not symmetric because AB, okay, so I'm gonna explain here. Because AB is in R, but BA is not in R. It's the short way of saying BA is in R is false, but you know, it's just me being lazy so that I don't have to say something is false. All right. Do we have any questions about symmetry as a property of a relation? Okay, we got some questions coming, hopefully. You guys can type an example too, you know, in the text channel, or take a screenshot if you're using a piece of paper or a tablet yourself. So that way we can just kind of work on what you guys have questions about. It's like, okay, what about this one then? All right. The last two. Okay, so the way we want to evaluate, you know, in this case, you know, the for all, which is EF in X, is basically we have a double loop. Okay, so we basically bind E to one of the elements first. Okay, so E can be bound to A first, and then while E is bound to A, we bind F to also A, and then we evaluate the condition. We evaluate this condition over here. So when E is A and F is A, let's take a look at this relation first. Okay, when both are A, we basically say AA is in R is false, but then AA is in R is also false. So that means the expression ends up being true. Okay, I'm just going to put a T here, you know, to indicate the result of the expression that we have quantified. But when E is A, F can also be B, right? So now we look at the case where E is A and F is B, and we go like AB is in R is true, and then BA is in R is also true. Okay, so we got true over here. And then what we do is we get out, because we have exhausted everything that F can get, because there are only two elements, so we go back to the outer loop, and then this time we bind E to B. When E is B, we look at F again. F can be A. So now we evaluate BA. Okay, this is BA is in R, that is true. This is now AB is in R, which is also true. And then we bind F to B now. So now we have BB is in R is false. BB is in R is also false, but false if and only if false is true. So the expression still evaluates to true, and then now we are done with the double loop. Okay, and when we're done with the double loop, we look at the result of each evaluation of this expression, and they are all true. And as a result, this R is indeed symmetric. Is that okay? All right, cool. So you basically apply the same idea to this R here. So if you apply the same to this R here, you will find that, okay, so I'm just going to be lazy and only erase the result. Okay, so we'll go ahead and evaluate again. Okay, so we'll start with E and F both being A. So AA is in R, yes, true. AA is in R, true. True if and only if true is true. So for this particular case, the answer is true. Okay. Now we bind E to A, F to B. Okay. So now we have AB is in R. Oh, okay. You guys cannot see my pointer. So now we have AB in R that is true, because we do have AB here. And then we have BA in R that is false. So we have true if and only if false. That makes the if and only if false. Now, I can go through all of the other ones, but in a for all quantified statement, if at least one case is false, the entire thing is going to be false. So I can just do a short-circuited exit at this point and just say that this particular R over here is not symmetric. Alright? So we kind of okay with symmetry at this point. Alright? It makes more sense. It takes a little bit of time to really kind of relate all of those concepts that we have already introduced up to this point. I sequence those topics in this particular way, because I really need to define the operators and then the quantifiers, and then now we basically make use of both at the same time. Alright, so let's take a look at the next one. The next one is transitive. Okay, so we are basically looking at a relation to see whether it is transitive or not. So once again, I'm just going to read this out first. A relation R over a set X is transitive if and only if the following is true. So now we have a even longer expression. And this one is kind of tricky too, because the other two, one is really easy. Okay, the first one is super duper easy because it just wants the membership to be true for each iteration of this loop. Okay, we got that. The second one gets a little bit more complicated because it's a double loop and we are using if and only if. You can sort of look at if and only if as equality. Okay, if the left hand side equals to the right hand side, then the operator returns true. If the two sides are different, it returns false. You can sort of look at it that way. And if you do look at if and only if, like just a straight up equality, which is equal in C and C++, yeah, things get it's okay. I mean, we can understand that. But this time we have implies, okay, which is a little bit harder to grasp, and we have a conjunction on the left hand side as the precedent of the implication. So this gets a little bit complicated. Okay, it can be complicated, and in past semesters, when people have this on the exam, it is transitive, and also anti-symmetry that is harder for people to grasp. Okay, so we'll open the new page on the tablet, and I'm just trying to see if I should copy the equation. Okay, this time I'll do it this way. I am going to resize the tablet until I can fit the quantified expression. Alright, so it's not cooperating because it's not scrolling in steps that I want. There we go. Okay, now we can look at this and make it slightly bigger. There we go. Okay, excellent. So this way I don't have to copy, and you get to see the statement when we work on our example. So we'll have x equals to a, b, and c. Okay. And once again, we look at the empty relation first. So the question is the empty relation transitive? In other words, if I were to evaluate this quantified statement, when x is defined to be a set with a, b, and c as elements in it, and R, the relation defined over X, is empty, is the empty relation transitive? That is now the question. The answer is yes. Okay, very good. So Jack is correct. So the answer is yes. Okay, so this one is actually pretty easy to see. Okay, so I'm gonna tell you why it is easy to see. Because it doesn't matter what E, F, and G are bound to, because R is empty. So every single element of R is going to be false. Okay, so this is going to be false, this is going to be false. As a result, the conjunction is going to be false. Well, if the left hand side of an implication is false, the implication itself is going to be true. So that means no matter what we bind, how we bind E, F, and G to, the implication is guaranteed to return true. So that means, the whole quantified expression is going to be true. And that's why R as an empty relation is automatically transitive. Are we good so far? Or are there any questions about this? Alright, so we are good. But I do know that someone is already thinking or asking this question in their head, go like, but I don't really quite get it. How come if the precedent or the left hand side of the implication is false, then the implication itself is true? Well, that is defined. That's how it is defined. Okay, the implication operator has its own truth table. So if anyone has that question, my recommendation is really to go back to the definitions of the operators, so that those operators are well defined in your head, because it is really kind of important at this point of time to really understand all of those operators. Alright, so let's move on. Let's look at another R here, and we'll make this one AB and BB. Okay, that's it. And the question is this one transitive? Yep, Jack is right. This one is also transitive. And somebody's going to say, but C is not even mentioned anywhere within R. It doesn't matter. Okay, it does not matter. Now, for those of you who think, I don't think so, I don't think this R is transitive. If that is what you're thinking, then you have to ask me in the text channel and say, what if E equals to this, F equals to this, and G equals to this? Doesn't that make the expression, all the way on top here, doesn't that make this expression false? That is how you want to increase your understanding of the concept, is to say, I don't think it is transitive because when E equals to this, F equals to this, and then G equals to this, I think this condition is going to be false, and as a result, the universally quantified statement itself is going to be false. But if you cannot come up with an argument like that, then we have to say, well, R is going to be transitive. Are we good so far or not? Alright, so let's take a look at the third one. This one is tricky. What about this? Is this R transitive? This one is a little bit tricky, but not too tricky. Damon is correct. This is not transitive. Yep. They go like, okay, this is not transitive. Why is it not transitive? Well, we can now specify, values of E, F, and G so that the expression in the notes here is false. Okay, this one is actually pretty easy to show. So in order to show this R is not transitive, think about what happens when E equals to A, F equals to B, and then G equals to A again. Okay, so in that case, what do we have? We have AB in R. Okay, that's one side of the conjunction, and then the other side of the conjunction we have BA in R, and then the entire conjunction is implying that we have AA is in R. Okay, so this is what happens when we have E being A, F being B, and G being A again. So we have true, so the conjunction is true. This one is false. So now we have true implies false, and that is false. True implies false has a value of false. And because there's at least one example where the implication is giving us a value of false, so that means the universally quantified expression, which is defined up here, is also false. How did I get that? It's just an example, because the only restriction about E, F, and G is, they all have to be elements of X. Well, A is an element of X, so I can. There's no reason why I cannot bind variable G to element A based on the universally quantified statement. If you think about this from the loop perspective, you have 3 times 3 times 3, there are 27 innermost iterations to evaluate. The outermost is going to be A, B, and C, and then while E is A, F can be A, B, or C, while E is A, F can be A, B, or C, and then when E is C, F can be A, B, or C. And then G is the last iteration. When E is A, F is A, G can be A, B, or C. This can be A, B, or C. This can be A, B, or C. Da, 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 da. Okay, so that illustrates why we have 27 innermost iterations. Because E is the outermost loop, F is the intermediate loop, and then G is the innermost loop. And then each loop has 3 iterations. So now you got 3 times 3 times 3, which is 27 iterations. And for each iteration, or for each innermost iteration, we need this condition to be true. If you can find at least for one of those iterations that the condition is false, then the universally quantified statement is false. So that's sort of that. I mean, I just picked an example to make it false, okay? But you can see that ABA is one of these things because we got A, B, A. So we know that is a part of the 27 innermost iterations of this triple loop construct. Are we good with this one? Maybe? I'll give you some more examples. What about the case when R equals to AB, BC, and AC? There we go. What about that? Is that transitive or not? The answer is it is transitive. Okay, this is transitive. So the way we look at this one is there's really only one special condition that we have to think about in this case, is when E equals to A, F equals to B, and then G equals to C. When that happens, then we have AB in R being true, And then when we have B, C in R, then that's also true. And then we have A, C in R, that is also true. Then we have true implies true, which is true, okay? Then what about all of the other cases, okay? For all of the other cases, the conjunction is going to be false. And if the conjunction is false, then we don't have to worry about the rest. Is that okay? All right, so I'm not. Okay, excellent. Then we are going to move on to anti-symmetry, which is also a kind of a weird definition. So anti-symmetric says a relation R over a set X is anti-symmetric if and only if the following is true. This one is kind of awkward because it says for all ways to bind elements of X into E and F, EF in R and FE in R implies E equals to F. That is really awkward. Alright, so let's go ahead and take a look at a few examples. Now once again, if you want to think of a particular example, you can always post your example in the text channel, so then we can take a look at that one and go like, okay, let's take a look at this one. If you're shy and you do not want to post it in the class channel, you can always direct message and send me the example, and then I'll put it into the tablet without mentioning any names, so that way you can stay anonymous if you want to. Alright, so we are ready for more examples, but this time we want to see if something is anti-symmetric. Alright, so we'll go ahead and start with X. This time we will use something simple again. So X is just a set with 1 and 2 in it. And as usual, we say, what about the empty relation? So is the empty relation anti-symmetric? The answer is yes. Very good. Okay, now how do we know that? Because if R is empty, then the element of here and the element of here, they're both going to be false because there's nothing in R, right? So that makes the conjunction also false because we have false and false. Well, when the left-hand side of the implication, which is the precedent, is false, then the implication itself is guaranteed to be false. And so as a result, basically we say it doesn't matter how you choose your E and F. If R is empty, then the left-hand side of the implication is going to be false, which means the implication is going to be true. So that means the universally quantified statement is going to be true. So the empty relation is indeed anti-symmetric. And don't be confused by the term anti-symmetric. It does not mean not symmetric. Okay, so there are two different things. Okay, so anti-symmetry is not suggesting not symmetric. Okay, it is defined a little bit differently. All right, so let's take a look at another R. So in this R we got 1, 2 in it. That's it. Okay, just 1, 2. So now the question is this anti-symmetric? What do you think? The answer is it is anti-symmetric. Anti-symmetric. All right. Yep. So Jack is the right answer as well. So now you go like, but why is it anti-symmetric? Well, because if you want an implication to be false, The only time an implication is false is when the left-hand side is true, but the right-hand side is false. So that means if you want a relation to be not antisymmetric, you need it to be you need to find how should I put it? You need to find two tuples where they are the reverse of each other, and that is how you make a relation not antisymmetric. Okay? So I'll give you an example. In this case, it's easy because we only got two elements, right? So this one is not antisymmetric. The reason why this is not antisymmetric is because if E equals to 1 and F equals to 2, then we have both element of being true, which means the conjunction is also going to be true. If the conjunction is true, then we have true for the left-hand side of the implication, but at the same time, E equals to 1, F equals to 2, 1 equals 2 is false. So that's why now we have true implies false, which basically means this R is not antisymmetric. Let's look at another example. Okay, what about we got 1, 1 and 2, 2 in this relation? Is this one antisymmetric? It is antisymmetric. Very good. Very good. So now the way we think about this is, can we make this conjunction true? Because if you cannot make the conjunction true, then the relation is going to be antisymmetric. Okay, the only time when it cannot be antisymmetric is you can find a case to make the conjunction true but the equality false. That's the only time you can say a relation is not antisymmetric. So in this case, yeah, indeed, we can make this conjunction true, but that happens only when E and F are both 1 or E and F are both 2. So, and when E and F are both 1, you can say 1, 1 is in R is true, 1, 1 is in R is true, and guess what? 1 equals to 1 is true too. So we have true implies true, so that means it's, we cannot make it false, right? So the other time is when E and F are both 2, same argument, the implication is also going to be true. What if E and F are different? What if E is 1 and F is 2? Well, if E is 1 and F is 2, then the membership is going to fail. If the membership is failing, then the conjunction is going to fail, meaning it is going to be false. Then you have a false on the left-hand side of the implication, which means the implication is going to be true. So that is the key of how we evaluate whether a relation is antisymmetric or not. And Aiden is typing something, so we'll go ahead and wait. Okay, so the question is, antisymmetric but not reflexive is the same as not symmetric. They are indeed related in some way. I just haven't thought about it this way. So certain combinations is not possible. If you look at all the properties that we have talked about so far. So we have talked about reflexive, we talked about symmetric, we talked about transitive, and also we have talked about antisymmetric. So there are certain of these that cannot mix in a certain way. I'm not really sure whether it is the case, whether Aiden's case is automatically true. It is actually not true. Something can be anti-symmetric, not reflexive, and yet also symmetric at the same time. So it doesn't guarantee what you end up with is not symmetric. The empty relation is an example because the empty relation is anti-symmetric, it is not reflexive, and at the same time symmetric. There you go. The empty relation is very interesting because of the way we define these properties. Yep. All right. So we got 10 more minutes. I think we can finish this entire module today. So yeah, I have to use the ping, tool to find my mouse pointer because it's just not easy to find. It is very precise. I know exactly what spot it is going to click on, which is why I choose the mouse pointer to be like this. But at the same time, it's a little bit harder to find if I just kind of move it around too much. Alright, so we now get to the definition of partial ordering. So partial ordering is defined based on the terms that we have already defined at this point. So a set X is said to be partially ordered by a relation R if and only if the following is true. R is reflexive over X, and R is anti-symmetric over X, and R is transitive over X. So in other words, when R is all three, reflexive, anti-symmetric, and transitive over X, then X is said to be partially ordered by this R. Alright, so now the question is, how is this helpful? Okay, so this reminds me, I'm using this as an example, because there was a beer commercial that basically says, it uses the words smooth and rich. Okay, so if you want to look it up, you can find it too. I think it's an Australian beer. Australian beer commercial, and then it mentions the word rich and smooth. There we go. So you can watch this on your own, okay? But you can definitely, it's kind of entertaining. But the idea is there are 4 ways to arrange, rich versus smooth. So what I do is you can read the text, okay? But I'm going to use the tablet to show you those 4 cases. So I'm going to make a sort of a truth table out of this. So we have rich, and then we have smooth. So we have true, true, false, false. Then we have true, false, true, false. So there are 4 ways to arrange. Okay, and the beer commercial talks about a character. Okay, so we have a character. They didn't mention anyone who's false to both, but they mentioned 2 examples where someone is rich but not smooth, and then someone who is smooth but not rich. Okay, so that's the funny part of the commercial is they show that you can find people who have one but not the other one. And of course, the beer itself is both rich and smooth, which is the whole point of the commercial. Is this beer is the ideal beer because it is both rich and smooth. I actually do not drink, so that's the funny part. But I do enjoy commercials that are funny. And then there are people, characters who are neither rich nor smooth, and they were not mentioned anywhere in the commercial because that would be pointless. So I'm just going to define, is at least as attractive as using these terms. Okay, so I'm gonna use a relation that is is at least as attractive as. Okay. This is the relation we want to define. Now, obviously, I'm using a really materialistic and, overgeneralized, way of evaluating attractiveness. Okay, so this is not what I'm suggesting that what attractiveness should be defined. I'm simply using this as an example. Okay. So now we have these four cases. So we have A, B, C, and D. Okay, and we want to define, how they relate. So we'll just basically say R, our relation, that we want to define is basically saying, A, B, C, or D is at least as attractive as, and then A, B, C, or D. Okay. So there are 16 possibilities, right? So if you want to enumerate all 16 possibilities, you can do that. But it's going to be a, well, why don't we do that? Just go ahead and do that, right? So we got A, B, A, C, A, D, B, A, B, 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 C, B, D, C, A, C, B, C, 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 D, and then D, A, D, B, D, C, and then D, D. Whew, okay. And now we want to define whether R should be true or not. Okay, this is X, this is Y, this is X, R, Y. Okay. So if you are comparing two characters who are both, rich and smooth, then the answer is, one is at least as attractive as the other one, right? Okay. And then when you have A and B, then you're asking, is someone who is rich and smooth at least as attractive as someone who is rich but not smooth? The answer is true. And then we have AC, which is comparing someone who is rich and smooth to someone who is not rich but smooth. But option A is at least as attractive as option C, so it is true. And then we have AD, which is obviously true. Okay. So now we have something that is not true, right? Because we have BA. So B is representing someone who is rich but not smooth, and we are asking whether that is at least as attractive as someone who is rich and smooth. That would be false. BB is always true, right? Because we are comparing the same qualification. BC is the one that we go like, put a question mark here. Okay, we'll answer the question mark later. And then BD would still be true. CA is going to be false. CB is going to be, we'll answer that question later. CC is guaranteed true. CD is guaranteed true. DA, the D, if you start with D, is always going to be false except for one of them, right? So this is false, 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 true. Okay. In other words, someone who is not rich and not smooth is at least as attractive as someone who is not rich and not smooth. Okay. So now we take a look at the question marks. Okay, so the question mark is basically going like, we don't really know. Okay, so if we don't really know, we answer false. Okay, because the question is at least as attractive as, and we don't know. There's really no actual ordering between those. So now you take all the true entries and then you put it into the relation. In other words, now we define R as a relation where we have A in it, AB in it, AC in it, AD is also in it, and then we have BB, right? And then we have BD, and then we have C, and then we have CD, and then finally we have DD in it. Okay, this is R. Okay, so what is the big deal here? The question is, we want to evaluate all of those qualifications that we have talked about earlier in today's lecture, and we are running out of time, darn it. Okay, so I'm not gonna take road today, so you guys everybody gets a free pass. But I know Wednesday is exam 1, so you may not have time to review this. But if you do, okay, and you might want to write this down so that you can do this after the exam, I want you to look at this R and answer these questions. Is this R reflexive? Is this R symmetric? Is this R transitive? And is this R anti-symmetric? So all of those are the kind of the ungraded assignment that I want you to do, is to evaluate all of the 4 qualifications to this particular relation. I know you may not want to do it until at least after the exam, but we are not going to meet, there won't be a lecture after the exam, so I cannot remind you to do this. So this is my reminder so that you can remember to do this kind of after the exam. And then we got one question coming before I stop the streaming. It looks like it's going to be a long question. Alright. Well, I'm not seeing anything appearing on the text channel, so I'm gonna stop streaming at this point. I will still have my office hour every day from 11 to noon time, so that's for tomorrow and also the day after tomorrow, which is the day when we have exam 1. So if you do have any questions, let me know. Oh, okay. Alright, so Lee Yu has a question about Aleph. No, I'm gonna stop the streaming, for now. If you want to kind of track that question, you can track it on the text channel. So I'm gonna stop streaming now.